so the current through them is the same. So 0.3 is going to give us, I think this is 2.5. So it means the PD across one lamp is going to be 2.5. Let's not use this because the connecting wires could be having some resistance. So the PD across is each lamp is going to be 2.5 volts since the connecting wires have some resistance. But the total PD of the three lamps, so it means the total PD of the three lamps is going to be 2.5 times 3 because they are identical. The PD across them should be the same. And I think this is 7.5 volts. It means there is some lost volts. 7.5 is not equal to 8.7. So the PD across the wires, the PD across the wire is going to be equal to the PD across the wires. There are two wires. The PD across the wires is going to be 8.7 minus 7.5, which gives us 8.7 minus 7.5, which gives us 1.2 volts. But there are two wires which are connected in series. They are just joining end to the end of the batteries of the bulbs. And we want the PD across each connecting wire. So we are going to divide by that by, the resistance of each connecting wire. So we have the PD, and we can have the total resistance of the two wires, which is going to be 1.2 divided by 0.3 because that is the current. So divide by 0.3, which gives us 4 ohms. That is total resistance. Then again we divide this by 2. So for one wire, it is going to be 4 divided by 2, which is equal to 2.0 ohms. Okay. The resistance of the metal of the connecting wires does not vary linearly with the temperature. On the figure 5.2, sketch the IV characteristic for one of the connecting wires. Of course, we are seeing that the resistance for one of the connecting wires is 2.0 ohms. That is the resistance, and that is going to give us the current. Let me see, current is equal to, if we say 2.0, so we say 4 divided by 2.0, that is going to be 2, so the gradient is going to be a half. So the resistivity of the metal of the connecting wires does not vary linearly with the temperature. So resistivity does not vary linearly with the temperature. On the figure, sketch the IV characteristic for one of the connecting wires. If the resistivity does not vary linearly with the temperature, many times the resistivity depends on the material. So it means the IV characteristic for one of the connecting wires is going to be a straight line in the first place. To be a straight line through the origin. However, the gradient will be is going to be lower. The gradient is going to be lower than the one that we already have there. So this is going to be a straight line because it is a connecting wire. So I'll have a straight line through the origin because it obeys Ohm's law. Okay, so connecting wires must be obeying Ohm's law at lower temperatures, unless when the temperature increases. So that will be a straight line. This is very vague. Okay, you can draw a better graph. You can draw a better graph than mine. So the graph is going to be a straight line. It is going to simply be a straight line to the origin, because the resistivity of the metal of the connecting wires does not vary with the temperature. It means resistivity is constant. And if resistivity is constant, we have that resistance is equal to rho L over cross-sectional area. R is constant. If the length of the wire is constant, the cross-sectional area is constant. It means resistance is constant. So that is going to be a straight line, which means I is directly proportional to V. I is directly proportional to V. So that would be just a straight line. It will be a straight line. Okay. Calculate the power loss in one of the connecting wires. Power loss in one of the connecting wires. So power is equal to I squared R. Power is I squared times R. And the current is 0.3, but is squared times the resistance of one connecting wire, which is 2. So that one we just substitute 0.3 squared times 2, which gives us 0.18. So this is 0.18. You can use another formula. So this is giving us 0.18, or you can say power is equal to I times V. But of course, you know that V is equal to I times R. So it means you will still have I times V, where V is I times R. So I times R is going to be 0.6, then times again times I, which is going to be 0.3. So this is going to be 0.3 times 0.6, which gives you 0.18. Alternatively, you would also use power is equal to V squared divided by R, which would be, and remember V is IR, so this would be I, which is 0.3, times R, which is 2. This should be squared divided by R, which is 2. It gives you the same thing. Okay, some data for the connecting wires are given below. Cross-sectional area is given as 0.4. Resistivity is given as 1.7 exponent negative 8. Number density of free electrons is 8.5 exponent 28. Calculate the length of one of the connecting wires. Okay, so we already know that resistivity is equal to rho L over cross-sectional area. They gave us the area, so we don't need to change diameter. So this means the length is going to be equal to R times A divided by rho. We now substitute. R is, the resistance was 2.0. Area is 0.4. We change it to meters, so that will be 0.4 times 10 power negative 6. To change it to meters squared, then divide this by the resistivity, which is 1.7 times 10 power negative 8. So we check, open brackets, 2 times 0.4 exponent negative 6 divided by 1.7 exponent negative 8. So that gives us 47.05, which is approximately 47. The drift speed of calculate the drift speed of a free electron in the connecting wires. We have current as never, I is equal to never. So the drift speed is going to be the current divided by NE times A. So the current is 0.3. The number of free electrons per unit volume has been given as 8.5 times 10 power 28. The charge of one electron, 1.6 times 10 power negative 19. Then the area has been given as 0.4 times 10 power negative 6. So we have 0.3 divided by open 1 bracket, 8.5 exponent 28, 1.6 exponent negative 19, 0.4 exponent negative 6, then close the bracket. So you have 0.0000, that's 1, 2, 3, 4, 5, 5.5 times 10 power negative 5. Two cells A and B are connected in a series with a resistor R of resistance 5.5 ohms, as shown here. A cell A has EMF 4.4 volts and a cell B an internal resistance 2.3 ohms. Cell B has EMF 2.1 volts and internal resistance 1.8 ohms. State Kirchhoff's second law. So Kirchhoff's second law, we have that the sum of EMFs, in a closed circuit is equal to the sum of potential differences, or sum of PDs. The sum of EMFs in a closed circuit is equal to the sum of potential drops, or potential differences, or potential drops. Okay. Calculate the current in the circuit. Let's see the circuit. So we are going to use Kirchhoff's laws, and I will just choose the current in the circuit randomly, and I will draw a loop there, which is anti-clockwise. The sum of EMFs is going to be 4.4 minus 2.1, because in moving in the anti-clockwise loop, I meet negative before positive, that EMF is positive. Here I meet positive before negative, that EMF is negative. The sum of EMFs is 4.4 minus 2.1. Then the sum of PDs is going to be, for cell A, it is going to be 2.3 times the current I, plus for cell B, it is going to be a negative, because no, it is not negative, it is positive. The current is in the same direction, so it is going to be plus 1.8 times I. Then we have 55, so that will be plus 5.5 times the current I. So that is the sum of the potential drops. So we are having 4.4 minus 2.1 equals to the current I into the sum of the resistances. We have seen we had 2.3 plus 1.8 plus 5.5. That is the sum of the PDs. So we just solve this. 4.4 minus 2.1 divided by, open brackets, 2.3 plus 1.8 plus 5.5. So that is giving us 0.24. So the current I is 0.24 amperes. On figure 4.1, draw an arrow to show the direction of the current in the circuit. Label this arrow I. So I think I've already labeled it. The current is in the anti-clockwise direction. Reason: the EMF here is greater than the EMF here, so it means the resultant current must be in the anti-clockwise direction, because the current through this battery is going this side. The current from this battery is supposed to be going that side, but since the EMF of this battery is greater than this EMF, so the resultant current is going to be anticlockwise. So the arrow is here. So that one is already labeled. Calculate the PD across resistor R. PD across resistor R. We have the current through the resistor. It is the same current that we have calculated, and PD is I times R, so I just multiply. PD is equal to I times R, which current is 0.24 and R is 5.5. So just press our calculator. 0.24 times 5.5, that gives us 1.32. Then calculate the terminal PD across cell A. Terminal PD across cell A. Terminal PD across cell A. So this is cell A. Terminal PD is the PD between the terminals of this cell. That means we shall get its EMF minus the PD across its internal resistance. That is, so the terminal PD is going to be the EMF of that cell minus the PD across its internal resistance. So PD, terminal PD across cell A is going to be its EMF, which is 4.4, minus the lost volts within it. So this is going to be 4.4 minus the current is 0.24. Remember, the lost volts is I times internal resistance. So this will be 0.24 times the internal resistance, which is 2.3. So the terminal PD will be 4.4 minus 0.24 times 2.3, which gives us 3.85. So that is 3.85 or 848. So that is 3.85 volts. Then calculate the terminal PD across cell B. Since I have the terminal PD across cell A, and I know the PD across the resistor R, then it becomes easy to find the terminal PD across cell B. I can just say terminal PD across cell B is equal to 3.85, which is the terminal PD across cell A minus the PD across the fixed resistor of 1.32. The balance is going to be the terminal PD across cell A. So that will be minus 1.32, which gives us 2.53. So this can be 2.53 volts. Alternatively, because the current is in the opposite direction to the current I have considered I is in opposite direction to the current through this battery, so I'll put a negative there. I'll say that the terminal PD across B is equal to its EMF, which is 2.1 minus the lost volts, but the current is in the opposite direction, so it will be minus negative of the current, which is 0.24 times the PD, I mean the resistance of the internal resistance, which is 1.8. So that means we have 2.1 plus the product of 0.24 times 1.8, which gives us 2.53. So this is 2.53 volts. So this will be method number 2. This is method number 1. Okay. A potentiometer circuit that is used as a means of comparing potential differences is shown in the figure down here. So that is the potentiometer circuit. A cell of EMF E1 An internal resistance R1 is connected in series with the resistor of resistance R1 and uniform metal wire of total resistance R2. So the wire has resistance R2. A second cell of EMF E2 and internal resistance R2 is connected in series with a sensitive ammeter and is then connected across BJ as shown there. The connection at J is halfway along the wire. The current directions are shown in the figure. If the connection is halfway, remember resistance is directly proportional to length. And the length of the wire was R2, so it means BJ, the resistance of BJ is going to be R2 over 2, and the resistance of JF is going to be R2 over 2 because resistance is directly proportional to length. Okay. Use Kirchhoff's laws to obtain the relation between I1, I2, and I3. So we come to the junction here. At B, you see I1 is entering, I3 is entering, I2 is leaving. So I2, the sum of currents entering is equal to the sum of currents leaving. So we shall have that I1, which is entering, plus I3, which is entering, should be equal to I2, which is leaving. Then between E1, R1, R2, R1, small r1, I1, and I2 in the loop H, H, B, J, F, G, H. H, B, J, F, G, coming back to H. So we ignore the bottom part. H, B, J, F, G, H. So we have ignored the bottom part. And note that these BJ and JF are acting as if they are resistors in parallel. The current in BJ is I2, I mean in series, but here there is a potential divider. The current in BJ is I2, but the current in JF is not I2, it is actually I1, because this current here is I1. I2 is not the same as I1 because there is a junction here, there is a junction here. Therefore, the sum of EMFs, there is only one cell, which is E1. Sum of EMFs is going to be E1, should be equal to the sum of PDs. Now let's see the PDs. We have a PD due to the small internal resistance. The PD here is going to be I1 times small r1. The PD for this one is going to be I1 times capital R1. And the PD for the metal wire JF is going to be I1 times R2 over 2. The PD for BJ is going to be I2 times R2 divided by 2. Now we look at direction. The currents are in the same direction as the loop. B, H, B, J, F, G, H. The currents are in the same direction as of the loop. So we just sum them up. Therefore, we shall have E1 is going to be equal to I1 times small r1 plus I1 times capital R1 plus I2 times R2 divided by 2 plus I2 again. Is it I2? No, this is I1. So this is again plus I1 times R2 over 2. Because the second part is current there is I1. Okay, so that is going to be our equation. That's going to be our equation. Then between E1, E2, R1, R2, R1, R2, I1, and I3 in the loop, H, B, C, D, J, F, G, H. Let's see. B, C, D, J, F, G, H. Coming back to, sorry, we said H, B, C, D, J, F, G, coming back to H. It means we have left out BJ. When we move from H, B, C, D, J, F, G, coming back to H, we have left out the resistance of R2/2, that is between B and J. Therefore, the sum of EMFs, we have two cells, E1, the loop is anti-clockwise, and E1, the current through E1 is in the same direction as the loop. But then for E2, the current is in the opposite direction, so this is going to be minus E2. So the sum of the EMFs is going to be E1 minus E2, E1 minus E2. Let's see the sum of the PDs. For the small r1, the PD is going to be I1 R1. For the capital R1, it is going to still be, so we have I1 R1 plus I1 capital R1. Then we come to the small r2, the current is I3 but is in the opposite direction to the loop. So this will be minus I3 times R2, small r2. Then we come to JF. The current is I1, so it is in the same direction as the loop. So this is going to be plus I1 times JF is R2 divided by 2. So we have many quantities with I1 as their current. We have this one, we have that one, we have that one. So the equation will be E1 minus E2 is equal to negative I3 times small r2 plus I1 in brackets small r1 plus capital R2, capital R1, then plus R2 over 2. Okay. So we are having our equation as E1 minus E2 is equal to negative I3 R2 plus I1 into brackets R1 plus R small r1 plus R2 divided by 2. So that's our equation. The connection at J is moved along the wire. Explain why the reading on the ammeter changes. Of course, when we move J along the wire, the reading of the ammeter is going to change because the PD across BJ is the same as the EMF. E2 is going to give us the PD across R2. And the PD across R2 depends on the PD across BJ. So moving J along BF, the PD across BJ changes. And when it changes, it means the current, the PD across R2 is also changing. So the current through the ammeter must also change. So we can say that the PD across BJ of the wire changes. That means the resistance BJ changes. Because the resistance BJ changes, the PD changes because the resistance of BJ changes when J is moved, because resistance depends on that length. So resistance of BJ changes. So there's a potential difference. There's a difference in PD across the wire and the PD across the cell E2. So there is a difference in PD across the wire because there has been a change in PD across the wire. Then it means the PD across the cell also changes. There is a difference in PD across the wire and the PD across the cell E2 and PD across the cell E2. So the ammeter reading must change. So the ammeter reading So the ammeter reading changes or must change because moving the connection J along the wire means BJ changes simply because its resistance changes. And remember, the PD across BJ is going to be equal to the PD across the cell E2. And therefore, the current through the cell must change. Okay. Determine the SI base units of resistivity. Okay, we can find this very fast. Resistivity from resistance is equal to rho L over area. It means that resistivity is equal to RA divided by the length. A is area, whose units are meters squared. L is length, whose units are meters. All we remain with is resistance, but resistance can be got from I squared, power over I squared. So power is I squared R, so this is resistance is going to be power over I squared, which we know power is energy over time, so I is going to be energy divided by time times I squared, because power is energy over time. And we know the units of energy, so the units of resistance are going to be those for energy, which is kilogram, meter squared per second squared, divided by T, which is seconds, times I, which is ampere squared. If you don't know how to arrive at the units of energy, you can get energy from work done, which is force times distance, which can be kilogram meters per second squared times meters. That's how I arrived at kilogram meters squared per second squared. So divide by S ampere squared. So resistance is going to give us kilogram meters squared per second cubed per ampere squared. So that means now the units of resistivity are going to be resistance, which is kilogram meters squared per second cubed per ampere squared divided by or times cross-sectional area, which is meters squared, divided by length, which is meters. So when we simplify, we have kilogram meters squared times meters squared divided by meters becomes meters cubed, then times S power negative 3, then per ampere squared. So this will be per ampere squared. So that is going to be the expression for resistivity per ampere squared. A cell of EMF 2 volts and negligible internal resistance is connected to a variable resistor R and a metal wire as shown in the figure below. The wire is 900 millimeters long and has an area of 1.3 times 10 power negative 7 meters squared. So we have the length, we have the area, we have the resistance of the wire is 3.4. Actually, the resistivity of the wire, so we have that resistivity is RA over L. R is 3.4 times the area, which is 1.3 times 10 power negative 7 divided by L, which is 900 times 10 power negative 3. 3.4 times 1.3 exponent negative 7 divided by 900 exponent negative 3. So that's 4.9 times 10 power negative 7. The resistance of R may be varied between 0 and 1500 ohms. Calculate the maximum potential difference and minimum potential difference possible across the wire. Maximum PD and minimum PD across the wire. When do we have maximum PD? So of course the maximum PD across the wire would be when R is going to be 0. If R is 0, then it means the PD across the wire, the metal wire is going to be just 2 volts. If R is 0, for R equals to 0, the PD across the wire is going to be resistance of the wire, which is, what is the resistance of the wire, which is 3.4, divided by total resistance, which is 3.4 plus 0, then times the voltage supply, which is 2. And that gives us the minimum PD as, the maximum PD as being 2.0 volts. That is V maximum. For V minimum, R must be equal to 1400. For R equals to 1500 ohms, PD is going to be equal to 3.4 divided by 1500 plus 3.4 times the voltage supply, which is 2. I'm using a formula of potential dividers. That is, V out is equal to the resistance over total resistance, then times V supply. This is going to be 3.4 divided by the sum of 3.4 plus 1500, then times 2, which is 4.5 times 10 power negative 3. So the minimum is 4.5 times 10 power negative 3 volts. Calculate the power transformed in the wire when the potential difference across the wire is 2 volts. PD is 2 volts. Okay. So power transformed is going to be equal to V squared over R, or I squared R. So V is 2 but is squared over R. The resistance of the wire is 3.4. So this is the easiest. 2 squared is 4 divided by 3.4. That is 1.2. So the power transformed is 1.2. You can use a different expression. Then the resistance R in C is now replaced with a different variable resistor Q. State the power transformed in Q for Q having 0 resistance. Q has 0 resistance, and we have that power transformed is equal to uh, V squared over R, and they are saying state the power transformed in Q for Q having 0 resistance. I know very well somebody will move very fast and say that, okay, when Q has 0 resistance, the power transformed is infinity because V squared divided by 0 is infinity. But I want you to note that this is only true. Power is V squared over R. That's when V is, remember, V is going to be equal to I squared times R. So when R is 0, then power is going to be 0 because the potential difference is going to be 0. So that if the resistance is 0, V is 0. That means the power is going to be 0. Or you can just use I squared R, where if V is 0, the power is going to be 0. So this is going to be 0. For when R equals to 0, the power is going to be 0. Then when R is infinite, when R is infinity, still from power equals to I squared R. When R is infinity, it means I is going to be 0. When R is equal to infinity, here I said when R is 0, PD is equal to 0. So power is 0. Here, when R is infinity, again current flowing is 0. When R is infinity, tends to infinity, the current flowing tends to 0. So still we notice that power will be equal to 0. So here the answer is also 0. On the figure, sketch the IV characteristic for a filament lamp. We have stated that very many times. Initially, it is easy for the filament lamp to conduct, but as time goes on, the resistance increases. When it reaches some point, when the resistance increases, then the current flowing becomes smaller. So we shall start with a line which comes from the origin and then it curves. After some time, it becomes hard for the conductor, for the bulb for the current to increase, because the filament lamp becomes warm, the temperature increases. So the curve will go like that. You can do a very smooth curve with a pencil. So you don't need to, you don't need to make this curve to be horizontal. It should start from 0, 0 and should be a smooth curve. Draw a smooth curve with a pencil, and the end section the end section so the end section never horizontal. Although we can agree that the resistance increases, we cannot reach infinity. That's why we can't make this line to be perfectly horizontal at the end. So it is just going to be a curve like that. This is not going to be, although the gradient is decreasing, it is not going to be horizontal. We cannot make it perfect horizontal, because horizontal would mean the resistance has reached infinity, yet we cannot reach infinity in that case. Okay, so that will be the graph. Explain how the resistance of the lamp may be calculated for any voltage from its IV characteristic. So that one is very simple. We don't need a gradient. We just need R equals to V over I. So using resistance is equal to V over I and taking coordinates, of V and I from the graph, taking coordinates from V and I from the graph, using R is equal to V over I and taking coordinates of V and I from the graph, we calculate the resistance. So for any voltage, we just get V over I. We don't get the gradient. We don't really necessarily get the gradient. We can just get V over I. Two identical filament lamps are connected first in series and then in parallel, as shown there. So we have two figures. The circuits are shown in figure 5.2 and figure 5.3. Let's say this is 5.2 and this is 5.3. State and explain why the resistance of each lamp when they are connected in series is different from the resistance of each lamp when they are connected in parallel. Of course, we know that when they are in parallel, they have a greater PD across them, which makes them hotter, or which makes the lamps hotter. Therefore, the resistance is going to be higher when they are in parallel, because resistance is directly proportional to temperature. When they are in series, the PD across them is smaller because the 12 volts is going to be divided. Therefore, the lamps will be relatively less hotter, so the resistance is going to be relatively lower. So you can say each lamp in parallel has a greater PD. Has a greater PD, that is of 12 volts, thus a greater current. Thus a greater current. Because their resistance has not changed. Each has the same the resistance as it had here. So thus a greater current. So each lamp will have a greater current, making the lamp hotter, or more power to be dissipated in the lamp, making the lamp hotter. And if the lamp becomes hotter, resistance is directly proportional to temperature. Thus resistance of the lamps thus resistance of lamps in parallel is greater. This question is not asking to compare total resistance of the lamps when they are in series over to the total resistance when they are in parallel. No. It is asking to compare the resistance of each lamp. So when you consider one lamp in series, its resistance is going to be lower than when it is in parallel, because each lamp in parallel has a greater PD, which means there is more current through that lamp, making the lamp to be hotter. And if it is hotter, then the resistance of the lamps in parallel is going to be greater than when they are in series. Each lamp is marked with a rating of 12 volts 50 watts. Calculate the total resistance of the circuit for the two lamps connected such that each lamp uses this power. So we note that power is equal to V squared divided by R. Power is V squared divided by R. And we can find the resistance of each power. We are looking at them when they are, okay. We want them to use this power. Each lamp is marked with a rating of 12 volts 50 watts. So the PD across each lamp will only be 12 volts when they are joined in parallel. So the resistance of each lamp is going to be 12 squared divided by 50, which is going to be 12 squared divided by 50. So the resistance of each lamp is going to be 2.88 for each lamp. The resistance is 2.88 ohms for each lamp. So we want to calculate the total resistance of the circuit for calculate the total resistance of the circuit for the two lamps connected such that each lamp uses this power. So since we want each lamp to use that power, then the total resistance is simply going to be this one divided by 2. So R in parallel, resistance in parallel is simply going to be equal to, okay, let me just do it like this. One over total resistance is equal to 1 over 2.88 plus 1 over 2.88, which gives us 2 divided by 2.88, because they should be in parallel. So total resistance, R total, is now going to be 2.88 divided by 2. So 2 point, okay, just say answer, divide by 2, which is 1.44. So this total resistance is going to be 1.44 ohms. For a cell, explain the terms EMF. EMF, I think we now know what EMF is. The energy converted from chemical to electrical when a charge per unit charge flowing through or around a complete circuit. Energy, sorry. So this is energy converted or transformed. Energy converted from chemical. Energy converted from chemical uh, to electrical. Per unit charge, per unit charge flowing through the cell or around a complete circuit. Per unit charge flowing around a complete circuit. Or per unit charge flowing through the cell. That is EMF. Then internal resistance, of course, resistance, this is the resistance which accounts for the lost volts in the battery or loss of voltage in the cell. So resistance of a cell, causing loss of voltage or energy loss in a cell. Resistance of a cell causing loss of voltage or energy loss in a cell, that is internal resistance. The circuit in the figure shows two batteries A and B and a resistor R connected in series. Battery A has EMF 3 volts and internal resistance 0.1. Battery B has an EMF of 12 volts and internal resistance 0.2. Resistor R has a resistance of 3.3 ohms. Apply Kirchhoff's second law to calculate the current in the circuit. So for the second law, we are going to choose a loop. I will choose a loop. I think let me choose a loop in the clockwise direction. No, let me choose it in the anti-clockwise direction. I'm choosing it in the anti-clockwise direction because I see the EMF of battery B is greater than the EMF of battery A, so it would give me easier positive values to use. So I choose it in the anti-clockwise direction. This EMF will be positive and this will be negative. So the sum of EMFs will be the EMF of B minus the EMF of A should be equal to the sum of the potential drops. The current is the same I. So total resistances, I'll just add them because they're in series. We have R plus 0.10 plus 0.20. So I'm just going to substitute. That is 12 minus 3 is equal to I into R plus 0. They told us that R has 3.3. So I will just substitute it here. So that is 3.3 plus 0.1 plus 0.2. I'll just press my calculator. 12 minus 3 divided by 3.3 plus 0.1 plus 0.2. So that is 5 over 2, which is 2.5. So the current is 2.5. Then calculate the power transformed by battery B. Power transformed. Power is E. Power transformed by the battery is E times I. The current of the battery is 2.5, so this is going to be 12 times 2.5. So times 12, I think that is 30. Calculate the total energy lost per second in resistor R and the internal resistances. Total energy lost per second in resistor R and internal resistance. So total energy lost per second, that is still power. So power is equal to I squared times R, where R is going to be the total R is going to be the total resistance. So this is going to be because we want total energy lost per second in resistor R. So R is the resistance of 3.3. So this is going to be current, which is 2.5 squared times 3.3. R is 3.3. So let's check this with the calculator. 2.5 times 3.3, 2.5 squared times 3.3. That is 20 total energy lost per second resistor R and the internal resistances. And the internal resistances. Okay. So I can come back here. This is 0.1 and the other one is 0.4. So we have 0.1 plus 0.2, that is 0.3. And these ones, this is lost within the battery. So we want total energy lost per second in resistor R and the internal resistances. So okay, so total resistance is 3.3 plus 0.3, that is 3.3 plus 0.3, which is 3.6. So this is 3.6, not 3.3. Okay, so that is 2.5 squared times 3.3, which is 22.5. That is 22.5. Yes. So power is I squared R, where R is total resistance is going to be 3.3 plus 0.3, which is 3.6. Alternatively, method number 2, this is method number 1. You can use power as being equal to V squared divided by R, where V is, I think the resultant EMF is going to be 12 minus 3, that is 9 squared, divided by total resistance, which is 3.6, which can check. 9 squared divided by 3.6, that is 22.5. It is 9 because when you look at the loop, the effective EMF is 12, that is if you consider 12 positive, and 3 negative because 3 is the other way around. In moving around the loop, 12 is positive, 3 is negative. So effective EMF is 12 minus 3. That's why I have 9 volts. 12 minus 3, which is 9 volts, so it is 9 over 3.6. Okay, the circuit of the figure may be used to store energy in battery A. Suggest how your answers in B support this statement. Of course, we notice that the power which is supplied from cell B is greater than the power in cell A. It is even greater than the energy lost per second. That means some energy which is generated from B can be stored in A, because the power the power supplied by B is not all dissipated in resistor R, is not all dissipated in the internal resistor of B. So part of it can now be stored in A. Okay, so we are saying the power supplied from cell B is greater than energy lost per second in the circuit. Hence, some can be stored in A. Hence, some energy can be stored in A. Hence, some energy can be stored in A. We can check this. The power supplied from A, I think from B, is 30 watts, and yet the energy loss per second, which is the power loss per second, is 22.5. So that means if this is the energy power lost per second in R and the internal resistances, it means the surplus energy can now be stored in resistor in cell A. Okay. A variable resistor is used to control the current in a circuit as shown in the figure here. The variable resistor is connected in series with a 12 volts power supply of negligible internal resistance, an ammeter and a 6.0 resistor. The resistance R of the variable resistor can be varied from 0 to 12 ohms. The maximum possible current in the circuit is 2 amperes. That is 12 divided by 6 when R is 0. That is the maximum. Calculate the minimum possible current. The minimum will be when R is maximum. So the minimum current is equal to EMF divided by total resistance. So the EMF is 12. Total resistance will be 6 plus R, which will be 12 because they will be in series. 12 divided by 18, that is 0.67, because it is 0.66 recurring. On the figure 5.2, sketch the variation with R of current I1 in the circuit. Variation of R, that is variation of the resistance with the current I1 in the circuit. What happens to I1 as, what is I1? What happens to the current I1 as R increases from 0 to 12? So our graph is going to stop at 12, somewhere here. Our graph is going to stop at 12 ohms because the other one is varied from 0 to 12. So your graph should not go beyond that. But at the minimum was 2. So when R is 0, the minimum is 2. The maximum was 2. And when R is 12, we are seeing that this is 0.6. So 1, 2, 3, 4, 5, 6. 0.6 could be in this part here. 1, 2, 3, 4, 5, 6. 0.6 is around there. So we are going to join these 2 points, this one and that one, get a curve, that is a smooth curve. cannot be a straight line. And its gradient must be decreasing because as resistance increases, this graph would look like this. Yeah, so when R is 0, we have seen that when R is 0, the current is 2.0, and we have seen that when R is 12, the current is 0.67. So the graph is there. So it should be the curve should be like that, but should have a decreasing gradient. It may not become 0, but the gradient decreases. The gradient is decreasing. Then the variable resistor in A is now connected as a potential divider. We can see that in the diagram. It is now a potential divider as shown there. Now when it is a potential divider, here the dynamics change. Capture the maximum possible and minimum possible current I2 in the ammeter. So when we bring I2 is going to be minimum when we bring this one at the end. That is when R is 0. And when R is 0, it means the potential difference across it is 0, and it is the same PD across this one. So it means the minimum is going to be 0. So for I minimum is going to be equal to 0 because the PD will be equal to 0 across R when R is 0. Its PD is going to be 0. When R is 0, because they are connected in parallel with the 6 ohms, its PD is going to be 0. The PD across it is going to be 0. And if the PD across it is 0, it means the minimum current is going to be 0. And then for the maximum, R is going to be maximum. And remember, R is in parallel with the 6 ohms. So the maximum PD, I maximum, no, this is not true. Because they are brought in parallel, if we move this to the end, it means the PD is 0. That means I is going to be equal, because I is view over resistance. The only resistor acting there is 6. So it means this is going to be, I is going to be equal to 0 over 6. That's 0. But now, for maximum PD, this is going to be 12 divided by 6, which is going to give us 2.0. So the maximum current is going to be 2.0 amperes. So that is the maximum. Because the question was telling us that the variable resistor in A is now connected as a potential divider. It is connected as a potential divider. It divides potential. As shown here, remember that this varies between 0 and 12 volts. Ohms. It varies between 0 and 12 volts. So the first question was asking us to find the maximum possible and the minimum possible current I2. When the current reaches here, it is dividing. That is, it takes this path and also takes that path. If the potential difference across this is 0, it means no current is going to take this path. No current will take that path. It means all the current which is being generated here is actually going into the 6 ohms. And when the potential difference, when the resistor of this is maximum, when the resistor of this is maximum, then the current is going to divide here. The current is going to be divided there, and the maximum current will simply be 12 divided by 6, which is actually going to be um, 2. It is going to be 2 amperes. Sketch on the figure 5.4 the IV characteristic of a filament lamp. IV characteristic of a filament lamp. Of course, we know that initially it is going to be a straight line, or it is just a smooth curve starting from 0, 0, but the gradient is going to be decreasing, and avoid making the line to become horizontal, because horizontal means we have reached infinite resistance. So I'll just draw a smooth curve whose gradient is decreasing. So that is going to be our graph for the IV characteristic of a filament lamp. Okay. A resistor of resistance 6 ohms is replaced with a filament lamp in the circuit. And the figure 5.3 state an advantage of using the circuit of figure 5.3 compared to the circuit of figure 5.1. When using the circuits to vary the brightness of the filament lamp. The 6 ohms is replaced with the filament lamp. Of course, when we connect the filament lamp here, in this case, it will have full brightness because it will be in parallel. It will be in parallel. If if a filament lamp is here, where there is a 6 ohms, it is going to be in parallel with the power supply. When R is maximum, it means the PD across R is the same as the PD across the filament lamp, and it will be 12 volts. Of course, the current is going to be 12 divided by I2 is going to be 12 divided by 6, like we had done it here. I is 12 divided by 6 because the PD will be the same. That means the filament lamp will have full brightness, but we can also have ranges from full brightness to almost no brightness. That is also very possible depending on what we want. So a full range of current or PD is possible, ranging from 0 to a maximum value. A full range of current, or PD is possible, ranging from 0 to a maximum value. Ranging from 0 to a maximum value, which means our brightness ranges from off to full brightness, which means brightness ranges from from off. That is when the PD is 0 to full brightness. Yeah, the brightness of the bulb of the lamp will be it can range from 0 to full brightness, because the PD across the lamp will vary between 0 and full brightness. Okay. A circuit used to measure the power transfer from a battery is shown in the figure. The power is transferred to a variable resistor. of resistance R as shown here. The battery has an EMF E and internal resistance R. There is a potential difference V across R. The current in the circuit is I. By reference to the circuit shown in the figure, distinguish between the definitions of EMF and PD. So PD is across R and EMF is across the battery. So EMF is energy converted from chemical to electrical point charge, and PD is the energy converted from electrical to other forms such as thermal point charge. So EMF is energy converted from chemical to electrical point charge, and then PD is energy converted from electrical to thermal point charge. Use Kirchhoff's second law. Using Kirchhoff's second law, determine an expression for the current I in the circuit. So there's only one battery. Sorry. Sorry about that. There's only one cell, so EMF is simply going to be E. I will choose a loop. I will choose a loop in the anti-clockwise direction. So the EMF is going to be E. My pen is running out. EMF is going to be E. Sum of PDs, we have this one here, and we have this one. So if I choose the direction of the current as being downwards, so if I choose the direction of current as being downwards, then the EMF is going to be the sum of the PDs. Sum of EMFs is equal to sum of PDs. So we have I times R plus the current is I plus I times small r. Okay, so this means the equation is going to be E equals to I into R plus small r. So the equation is E is equal to I into capital R plus small r. Okay, so that is the equation that we want. The variation with the current I of the PDV across R is shown in the figure here. So it is a voltage, it is actually an IV characteristic, although it is now V against current. Use the figure 4.2 to determine the EMF. Use the figure 4.2 to determine the EMF. Of course, we know that EMF E is equal to potential, that is terminal PD plus the lost volts. terminal PD plus the lost volts. Sorry. So it is terminal PD plus the lost volts. That is EMF, E. Terminal PD plus the lost volts. And this means the EMF is equal to V plus the lost volts, which is current times R. So it means when the current is 0, when I equals to 0, it means E is equal to the PD, the terminal PD. So from the graph, we look for when current is 0. When current is 0, E is going to be equal to the PD, which here is, the scalar is 2 divided by 10, 0.2. So this is going to be 5.8. So the EMF is going to be 5.8. Then determine the internal resistance R. So we can first of all find the lost volts. We have seen the PD across the terminal PD. So we can find the lost volts. The lost volts, or we can simply say EMF is equal to the terminal PD plus the lost volts. The EMF we have said it is 5.8. Terminal PD. Oh, we don't have terminal PD. So let's find data for the gradient. Let's find the gradient. Let's just find a gradient because there's no any other way we are going to find a terminal PD. So I'm going to make a V the subject, and you see V is equal to E minus I times R. That means the gradient is going to be negative R because it is a graph of V against I. It means the gradient is equal to the negative R. Gradient is equal to the negative of R. So let's find the gradient. So I'm going to choose 2 points on the graph. Let me take 5.8 and I think I should take 2. This one here. Okay. So I'm taking the gradient. So this is going to be equal to the gradient is equal to the y-axis. We shall have 2.0 minus 5.8 divided by, this is 2.1 on the x-axis. That is 2.1 minus 0. So let's check. So 2 minus 5.8 divided by 2.1. That is negative 26. Is it? Two minus 5.8 divided by 2.1, negative 1.8. Remember the gradient is this, so this is equal to negative R. So negative 1.8 is equal to negative R, so R is going to be 1.8. Okay. So I just compared this equation with y equals to mx plus c. On the y-axis we have v, on the x-axis we have I. It means the gradient m is negative R. So the gradient is negative 1.8, so R is going to be 1.8. Using data from the figure, calculate the power transferred to R for a current of 1.6 amperes. So power transferred is equal to I times V, where I is 1.6 and V, they said use data from the figure 4.2. So let's say 1.6 I is 1.6. Let's find the PD across R. So 1, 2, 3, 4, 5, 6. So 1.6 is here. And it is in the center of that box. It is in the center of the box. 2.2, 0.4, 0.6, 0.8. So that is 2.9 in the center of the box. So that is 2.9. So 1.6 times 2.9. So that is 4.64. Approximately 4.6. Okay. Oh, by the way, I've even remembered in the part 2 of this equation, we could also find the resistance from the EMF is equal to the terminal PD, which terminal PD can be obtained from the current. The current is the same. That is 5.8 equaling to 4.0 plus 1.0 R. That means R is going to be 5.8 minus 4.0 divided by 1.0, which is going to be, I think, 1.8. 5.8 minus 4 divided by 1.8. Okay, but the easiest is, the most direct one is when you just find a gradient. You just find a gradient, because most of us may not be able to use this. But of course, what I just did is that I could choose the formula V equals to E minus IR, and I take the EMF is 5.8. V, I take V with its corresponding value. So if I take V as 4, its corresponding value is 1. So I'll say V is 4, I is 1 times R, which gives me R as 1.8. I just substitute in that equation corresponding values from the graph, but the gradient is fine. Okay. Use your answers from C Roman 1 and D Roman 1 to calculate the efficiency of the battery for a current of 1.6 amperes. Efficiency of the battery. So we know that efficiency is equal to power output, which is I times V, over power input, which is I times E. So I cancels. V is the terminal PD. When the current is 1.6, that was 2.9, divided by the EMF, which is 5.8. So that is 2.9 divided by 5.8. I think it is 50, or 0.5. Sorry, this is 0.5, but the answer as a percentage. So that is 50. Okay, the figure 5.1 shows a 12 volts power supply with negligible internal resistance connected to a uniform metal wire AB. The wire has length 1 meter and resistance 10 ohms. Two resistors of resistance 4 ohms and 2 ohms are connected in series across the wire, as shown here. Use Kirchhoff's first law, that is sum of currents into a junction equals sum of current out of the junction, to state the relationship between I1, I2, and I3. So you see I1 is entering, I2 is leaving, I3 is leaving. Therefore, I1 is equal to I2 plus I3. Then to find calculate I1. Calculate I1. So I1 is actually the total current. I1 is actually the total current. I can easily find, you notice that AB is in parallel with the two resistors, so you can find the current in each, and then you sum up. For example, I can say that I2 is going to be the resistance, the PD, which is the EMF, that is 12, divided by, I'm using I is equal to V over R, divided by the resistance of the wire, which has been given as 10 ohms. The resistance of the wire was given as 10 ohms. So AB, wire AB, the current is 1.2 amperes. Then we can get I3. The PD is still 12. The resistance is 6, which gives us 2.0 amperes. So we can say I1 is the sum of the two, which is going to be 3.2 amperes. So the current here is 3.2 amperes. Alternatively, we can use the concept of resistance. We can use the concept of resistance, where we know that the two resistors, AB and the other series resistor, they're in parallel. So total resistance in total is going to be the product, that is 10 for the wire times 6 for the two resistors over 10 plus 6. That's total resistance, which is 60 divided by 16. That is total resistance. Then to find total current I is equal to the EMF, which is 12, divided by total resistance, which is 60 over 16. So we have 12 divided by 60 over 16, which gives us 3.2. Calculate the ratio X, where X is power in the metal wire over power in the series resistors. Ratio X, where X is the power in the metal wire over power over the power in the series resistors. So power is IV or I squared R, whichever. So we can say power is going to be I squared R. I'll use that one. So you can use any other, or you can use I times V, or you can use V squared over R. I'll use I squared R. So the ratio X is going to be in the metal wire, which will be current in the metal wire, which is I2 squared, times the resistance of the metal wire, which I'm calling R wire, divided by the series. The current is I3 times the resistance in series. So this is going to be, we have seen I2 is 1.2 squared times the resistance, which is 10. Then I3 was 2.0 squared times resistance in series, which is 6. So that is 1.2 squared times 10 divided by 2 squared times 6, which is 0.6. So this is 0.60. You can use another method to find the same answer. You can use IV, you can use V squared over R. Calculate the potential difference between the points C and D as shown in the figure. The distance S is 40 centimeters and D is the point between the two series resistors. So we want the potential difference between C and D. That is very easy. We want difference in potential. So we want the potential difference between these 2 points. So we can find the potential difference between A and D and the potential difference between A and C, and we subtract. Or we can find the potential difference between B and D and the potential difference between B and C and subtract. It will give us the same answer. So whichever you think is easier. So potential difference between CD is going to be potential difference across AD minus potential difference across AC. You don't mind about the negative, the magnitude is the same. We just want a difference in potential. Remember, potential is equal to I times R. So potential difference across AD. The current is I3, the resistance is 4. So that is going to be 4 times 2, which is 8. Potential difference between AC. The current is I2, which I2 was, what is I2? I2 is, we calculated I2 was 1.2. So this is going to be 1.2 times resistance. So that I is 1.2. Resistance is going to be 40 over 100 times the resistance of the wire, which is 10, because the length is directly proportional to resistance. So the resistance corresponding to 40 centimeters will be 40 over 100 times the resistance of the whole wire, which gives us 4.8 ohms. So that means the potential difference is going to be just subtracting those two. Therefore, we are saying potential difference across CD, we said it will be potential difference across AD minus potential difference across AC. Potential difference across AD is the current, which is 2.0 times the resistance, which is 4, and that gave us 8 volts. Potential difference across AC is the current, which is 1.2 times the resistance, which is 40 divided by 100 times 10, and this gives us, I think, 4.8. So we want now the difference, 8 minus 3 minus 4.8, which is 3.2. So the potential difference between CD is 8 minus 4.8, which gives us 3.2. So this answer is 3.2. You could also have found the same answer using the other side. That is, you get potential between B and D. The current is I3, so that would be I3, and I3 was 2, so it would be 2 times 2, which is equal to 4 volts. Then the potential difference across CB, the current is I2, and I2 is 1.2 times the resistance of CB. If S is 60, CB is going to be 60 divided by 100 times 10, which is going to be 1.2 times 60 divided by 100 times 10, which is 7.2. So this is 7.2 volts. So the potential difference between C and D is going to be the difference between those two, which will be 7.2 minus 4, which is 3.2 volts. So that will be the potential difference between those two. Okay. Define resistance. People always prefer to define resistance in English as the opposition to flow of charge carriers, but now we cannot define resistance in English when we are answering physics. So we have to define this in physics. So resistance is going to be a potential difference over current, because R is equal to V over I. So we shall say potential difference per unit current. It will be potential difference per unit current, that is the resistance, or potential difference over current, that is resistance. A circuit is set up to measure the resistance R of a metal wire, the potential difference V across the wire and the current I in the wire are to be measured. Draw a circuit diagram of the apparatus that could be used to make these measurements. So we want to vary I and V to obtain R. Therefore, first of all, we need the wire. I will need a power supply. So let me have a battery. So I have a battery or a cell here. To measure current, I will need an ammeter. So I'll put a cell in series with the ammeter. Because I'm going to vary V, I'll need a variable resistor, that is maybe a rheostat, or I could use a variable power supply. So this is going to be in series with the wire. So I'll put the wire here. Okay, so I can measure the current in that wire. I have a variable resistor here, which is a rheostat. So because I need the PD across the wire, then I'll connect a voltmeter across. So as I adjust the variable resistor, I change V, and therefore I change the reading of the ammeter. So then I will plot a graph. So because this is not, the wire has no symbol, I will just label that as the wire. The rest are in their normal symbols, the known symbols, so I don't need to label them. This is a cell. We have a rheostat, a metal wire. I've just had to label the metal wire because I used a symbol which may not be the correct symbol for a metal wire. So the rheostat and the metal wire are acting as potential dividers, or I would have used a variable power supply to be able to vary the reading of the voltmeter V. Okay. Readings for the PD, V, and the corresponding current I are obtained. These are shown in the figure. So we see the line of best fit has been drawn, and we see that first of all, the values are scattering, and second, when V is 0, there is a current, which means there is a zero error. Explain how the figure indicates that the readings are subject to a systematic error. So we see that there is a y-intercept, so there is a zero error. The y-intercept on the graph shows there is a zero error. The y-intercept shows that there is a zero error. Then also we see that the values scatter around the line of best fit. So that means there is a random error. So scattering of readings about the line of best fit Scattering of readings around about the best fit line also indicates the presence of a random uncertainty. To use data from the figure, determine R, explain your working. So they said we must explain our working. So we shall simply use R is equal to V over I, and for V equals to, let's see an example for V equals to, I'm going to choose a value of V from the graph. I just choose a value of V from the graph. For example, let me choose 2.0. Then I is going to be 0.1234, 0.14. Then I subtract I will subtract the zero error. So this for V equals to 2.0 volts. The current I is going to be 0.14 minus the zero error, which is 0.05. This gives us 0.14 minus 0.05, which gives us 0.09. So this is 0.09 amperes. Therefore, the resistance is going to be 2.0 divided by 0.09. So 2 divided by the answer, that is 22.2. So this is 22.2. So this is 22.2. You can use any other point as long as you subtract the zero error from the value of current. You just subtract the zero error from the current value. In another experiment, a value of R is determined from the following data: I 0.64 plus or minus 0.01, V 6.8 plus or minus 0.01. Calculate the value of R together with its uncertainty. Give your answer to an appropriate number of significant figures. Okay, so let's find R. R is equal to V over I, which is 6.8 divided by 0.64. So 6.8 divided by 0.64, that is 10.625. 10.625. Then they gave us absolute uncertainties. So the absolute uncertainty in R is going to be equal to absolute in V over V plus absolute in I over I. Then this will be multiplied by the value of R. So the absolute in R is equal to, for V, 0.1 divided by 6.8. For I, 0.01 divided by 0.64. This is going to be multiplied by 10.625. 0.1 divided by 6.8 plus 0.01 divided by 0.64. Then times 10.625. So that is 0.3. So this is 0.322, but one significant figure is 0.3, which is one decimal place. So the answer will be 10.6 plus or minus 0.3. State Kirchhoff's first law. We have stated this law many times. By now you should be familiar with it. The sum of currents into a junction is equal to the sum of currents out of the junction. Sum of currents into a junction is equal to the sum of currents out of the junction. Then Kirchhoff's first law is linked to the conservation of a certain quantity. State this quantity. Of course, the first law is conservation of charge, as the second law is conservation of energy. First law, conservation of charge. Second law, conservation of energy. A variable resistor of resistance R is used to control the current in a circuit as shown in the figure here. The generator G has EMF 20 volts and internal resistance 0.5. The battery has EMF of 12 and internal resistance 0.1. The current in the circuit is 2.0 amperes. Apply Kirchhoff's second law to the circuit to determine the resistance R. So I'll choose a loop. I'll just choose my loop in this direction because I know I see this is positive, this is negative. So the EMF of the generator is going to be the effective, to cause an effective EMF. Therefore, using Kirchhoff's second law, the sum of EMFs is going to be equal to the sum of potential drops. So the EMFs, we're going to have 20 for the generator minus 12 for the battery. This is going to be the sum of PDs. We have the current is the same, which is 2.0. Then sum of the resistances, we have 0.1 plus 0.5 plus R, which is 0.6 plus R. The sum of resistances, because the current is the same, I just sum up the resistances. So I just get R with my calculator, 20 minus 12 divide by, divide by 2, again minus 0.6, which is 3.4. So R is 3.4. Calculate the total power generated by G. So power is equal to E times I. The EMF is 20. The current is 2. So that is 40. Calculate the power loss in the total resistance of the circuit. Power loss. Power loss in total resistance is going to be I squared times total resistance R. I is 2 squared into total resistance. We have 0.1 for the battery. We have 0.5 for the generator. We have the other resistor, which is 3.4. So this is going to be 2 squared times 0.6 plus 3.4, which is 16. So the power loss in the total resistance is 16 watts. The circuit is used to supply energy to the battery from the generator. Determine the efficiency. So we have seen the power loss as 16. That means the useful power is going to be 40 minus 16. So efficiency is going to be the useful power divided by the power input Of course, we may not multiply by 100. So this is going to be, the useful power is going to be 40 minus 16. And the power input is 40. So we can say 40 minus 16 divided by 40, which gives us 0.6. So this is 0.6, or it can be 60%. That is the efficiency. A battery of EMF 12 volts and negligible internal resistance is connected to two resistors and a light-dependent resistor as shown in the figure here. We can look at the figure. An ammeter is connected in series with the battery. The LDR and the switch S are connected across points X and Y. LDR is the light-dependent resistor. The switch S is open. Calculate the potential difference across XY. So since the switch S is open, I'm going to use the potential divider formula. That is PD across any point V out is going to be the resistance you want over the total resistance R1 plus R2, then times the voltage supply Vs. Or you can first find the current, the total current, and then you find the total PD. Okay, so total resistance is going to be 20 kilo ohms. The current I is equal to the EMF divided by total resistance, R total. The EMF is 12. Total resistance is going to be 8 plus 12 times 10 power 3. That is total current. Then the PD across XY. PD XY is equal to the current times the resistance of XY. So this is going to be 12 divided by 8 plus 12, that is 20, times 10 power 3, times resistance xy, which is 12, times 10 power 3. So 144 divided by 20, that is 7.2. So the PD is 7.2. Then the switch S is closed. The resistance of the LDR is 4 kilo ohms. Calculate the current in the ammeter. So if the switch is now closed, it means the LDR is in parallel with 12 kilo ohms. Total resistance here will no longer be 12. It has to change. So you have to get the resistance in parallel, which will be now 12 times 4 for the LDR, divided by 12 plus 4. I'm using resistors in parallel, so I'm finding total resistance as product over sum if there are only two. So this is 48 divided by 16. 48 divided by 16, I think that is 3. 48 divided by 16, that is 3. So the new resistance is going to be 3. That means now the current flowing, or the total resistance R total, is going to be 3 plus 8. Remember, this is in kilo ohms. 3 plus 8, which is going to give us 11 kilo ohms. That is the total resistance. If you want to find total current is going to be now 12 divided by 11 times 10 power 3. So they wanted us to calculate the current in the ammeter. The ammeter is in series with the battery, so that is total current. So that is 12 divided by 11 exponent 3, which is 0.00109, or 1.1 times 10 power negative 3. 1.1 times 10 power negative 3. The switch S remains closed. The intensity of the light on the LDR is increased. That means the resistance decreases. State and explain the change to the ammeter reading. So if the intensity is increased, the resistance of the LDR decreases. So resistance of LDR decreases. They are inversely proportional. The LDR, as the intensity of the light increases, the resistance of the LDR decreases. What happens to total circuit resistance? It decreases. So the total circuit resistance is going to be less. So R total is going to be less. So total circuit resistance, total resistance of the circuit is less. Total resistance of the circuit is less. Hence, if total resistance of the circuit is less, it means the current is going to be higher. Hence, current increases. So the current increases because the resistance of the LDR decreases when the light intensity increases. So it means the total circuit resistance, or total resistance in the circuit, is going to be smaller. And if total resistance is small, it means the current is going to be greater. So the current increases. Okay. Then how about the PD across XY? Now when the resistance of the LDR decreases, the PD across XY is going to be smaller because it's directly proportional to resistance. Therefore, resistance across XY, the resistance across XY is now less, or decreases, is now less, meaning it takes a less, remember the V across XY is going to be equal to the resistance XY over total resistance R total times the voltage supply of 12. That is times 12. So this means a less proportion of 12 volts across XY, meaning a less proportion of 12 volts across XY. Hence PD across XY is less. PD across XY is less. So the PD decreases, to be precise, when the resistance across XY decreases because the resistance of the LDR has decreased. It means that the PD across XY becomes smaller. That's what it means, because the PD is directly proportional to the resistance. Okay. The output of a heater is 2.5 kilowatts when connected to a 220 volt supply. Calculate the resistance of the heater. So they have given us V and the power. So resistance is going to simply be V squared over power, which is going to be 220 squared divided by 500, because it is 2.5 kilowatts. So 220 divided by 500, sorry, it is supposed to be 220 squared divided by 500, which gives us 19.4. So this is 19.4. The heater is made from a wire of cross-section area 2.0 times 10 power negative 7 meters squared. The resistivity is 1.1 times 10 power negative 6 ohm meters. Use your answer in Roman 1 to calculate the length of the wire. So we know that resistance is equal to rho L over cross-section area. So it means length is equal to R times A over rho. So we substitute. R is 19.4. Area is 2.0 times 10 power negative 7 divided by rho, which is 1.1 times 10 power negative 6. So this is 19.4 times 2 exponent negative 7 divided by 1.1 exponent negative 6, which is 3.53. 3.53 meters. The supply voltage is changed to 110 volts. Calculate the power output of the heater at this voltage, assuming there is no change in the resistance of the wire. There is no change in the resistance of the wire. So we know that power is equal to V squared over R, and there is no change in the resistance of the wire. So the resistance is remaining 19.4. So this is going to be 110 squared divided by 19.4. Okay, 110 squared divided by 19.4, that is 623 point something watts, or approximately 620 watts. State and explain quantitatively. So when it is quantitatively, you may quote a value. State and explain quantitatively one way that the wire of the heater could be changed to give the same power as in A. To give the same power as in A. Okay? So power, remember, is equal to V squared over R. We want to give the same power as in A. We want to change the heater so that it gives the same power as in M. If V is remaining the same as 110 volts, we can only change R, and R is equal to rho L over area, which is the same as 4 rho L over pi d squared. So we can change we need to change the resistance, which can be done by using a wire of a different length. That is, we can use a wire of a quarter of the original length, or a wire of area which is 4 times. Why should it be 4 times? The power here is 620, and the power before was 2.5. 500 divided by 620. That is approximately 4 times. If I had not used a rounded off value of current, I think I would get, this would have been 19.3. It was 19 point, let me see, 220 squared divided by 2500, 19.36. So if I use 19.36 here, let me use 36. 110 squared divided by 19.36. That would be 625 watts. This will not be wrong, but the other one is more exact. So I can use 625. And 625 is actually a quarter of 2500. So it means we need to make sure that R is reduced by using a wire whose length is maybe a quarter, so that we reduce, because when R reduces by a quarter, then power will be 4 times. So R needs to be reduced. R needs to be reduced by using a wire of length that is a quarter of the original length. A quarter of the original length, or the area, or we can use the area. Now, of course, area should now be 4 times. Area, which is 4 times, or area, which is 4 times greater. 4 times greater, or because the diameter is squared, so we can say wire of diameter, which is 2 times greater. Diameter, which is 2 times greater, because 2 squared will be 4. So that means it will be now 4 times when we square it. So R needs to be reduced by using a wire of length that is a quarter of its original length, because when R is reduced, the power is going to be increased. So if we use a wire of a quarter of the length, it means the power will be now times 4. If we use a wire of area 4 times greater, it means the resistance will be now a quarter, which means the power will now be 4 times. Or if we use the diameter, which is 2 times greater, it means the area will be 4 times greater, which means the resistance will be now a quarter, then the power will be 4 times. So we multiply this by 4. State Kirchhoff's second law. So Kirchhoff's second law is sum of EMFs is equal to the sum of PDs around a closed loop. Around a closed loop or circuit. Then Kirchhoff's second law is linked to the conservation of a certain quantity. Of course, I've been singing that the second law is linked to conservation of energy because EMF and PD, that is energy. The circuit shown in the figure is used to compare potential differences. Okay, so that is our circuit. The uniform resistance wire XY has length 1.0 meters and resistance 4 ohms. Cell A has EMF of 2 volts and internal resistance 0.5. The current through cell A is I. Cell B has EMF E and internal resistance R. The current through cell B is made 0 when the movable connection J is adjusted so that the length Xj is 0.9. So that means there is balance. The PD across Xj is going to be the same as the EMF of the cell B if there is balance. The variable resistor R has a resistance 2.5 ohms. Apply Kirchhoff's second law to circuit CXYDC. CXYDC, we ignore the lower part. CXYDP. I mean D back to C. CXYDC. So we have a loop here. I'll choose an anti-clockwise loop. There's only one cell of EMF, 2 volts. There are resistors. This is 1 resistor, that is 2, that is 3, the internal resistance. So we want to determine the current I. So sum of EMFs is 2.0. The current is going to be the same, so I just find the total resistance. We have for internal resistance, which is 0.5 plus R, so 0.5 plus R plus. For the wire was 4 ohms, so that will be plus 4 ohms. So this is the sum of the PDs. I times all those resistances, that is the sum of the PDs. So what is I? So I is going to be 2 divided by, no, not 2 divided by 2 minus, what is R? R is, I think R is 2.5. So let me remove R. It is 2.5. So I is going to be 2 divided by 0.5 plus 2.5 plus 4. So that is 0.286. 0.286 amperes. Calculate the potential difference across the length of wire xj, PD across xj. So to find the PD across xj, we may want the current times the resistance of xj. So let's begin by finding the resistance of xj. Xj has length 0.9 at balance, so it means the PD across it is going to be the same as the EMF of the cell without even wasting time. Let's find resistance Xj is equal to resistance is directly proportional to length, so this is going to be 0.90 over total length, which is 1.0 meters, times the resistance of the wire, which is 4.0. So that is the resistance of Xj. So which means the PD across Xj is going to be the current, which is 0.286 times the resistance, which is going to be 0. But this is the same as what? 0.9 times 4. That is 3.6. So times 3.6. So 3.6 times 0.286, which is 1.03. So this is going to be 1.03 volts. Use your answer in Roman 1 to state the value of E. So PD across Xj is the same as EMF at balance. So that means this is 1.03 volts. No need of any calculation. State why the value of the internal resistance of cell B is not required for the determination of E. Why don't we need internal resistance of the cell? At balance, they say the current through cell B is made zero when the movable connection J is adjusted. So when the current through B is zero, it means all the current I is flowing through Xj. That means there is no current here, so there is no lost volts here. Since there is no current through the battery, then it means the PD across R is zero, so it is not important. So we are saying since there is no current, through cell B, the PD across R is going to be zero. So the PD across R is going to be zero, so it is not required for the determination of E. I think that is enough for part 2, and watch out for the last part, which could be this is part 3. Watch out for part 4. Have a very blessed time. Bye bye for now.